image processing. So last time we had a first look at what images could be. So there are many very different varieties, from 1D signals to videos or volumetric images in 3 or more D. And we spent a considerable amount of time defining precisely what a discrete image is. So first, let's recall what we said is a continuous image. That's just a mapping from omega to R. So omega is our image domain, V is our value range, and this is a continuous image. Yeah, so that was very simple to define. For the discrete image, we had to set up a lot of notation. I just want to briefly remind you with the one sketch so that everybody has in mind how this looks. So we have to fix the dimension. That's 2 in this case. We have to specify what our image domain is. And I had this example that it's 0.8 times 0.6. So we have an 8 here, we have a 6 here. And to get a discrete representation, we still need to say how many pixels do we want in each coordinate axis. And this example, I took 4 in the horizontal and 3 in the vertical axis. So that means here we have our omega. We have 4 and 3 cells in vertical and horizontal axis. And we get a picture like this. We put our grid nodes in the center of these cells. Yeah, and in each cell, we say that the image has 1 value. And we call these distances here H1 and H2. Yeah, and then a continuous image here that is constant on each of the cells. So it has exactly 1 value in a cell and maybe another in a different cell, but in one cell is constant. This we call pixelated image. Yeah, to have a connection between our continuous world and the discrete world, where we then can think of the images as matrices. Yeah, because for the image, it's sufficient if you specify what the like the resolution and the domain is and what the value in each cell is. So the image itself is just a d-dimensional array with this extra information. Okay, and that's what we looked at last time. Some more remarks before we look at the first operators that can manipulate our images. And the first has to do with scanning. So how could you think of that these discrete images are obtained? So in digital images can be acquired by scanning. So what does this mean? So we start with a real valued continuous image. And if we now assume that we can integrate this image, so L2 just means square integrable. So the notation, hopefully everybody looked at the appendix by now a little bit. But if you didn't, just think about an image where you can integrate the squared intensity. So it has to be finite. And then we can get measurements as follows. So we integrate over the image domain our image, but we multiply it by some other function. Let's call that function psi. And just for briefer notation, this product integral is exactly the scalar product of these two functions in L2. What's the interesting thing is, what is this psi? How can we imagine what this is and how is it connected to how images are acquired? So this psi also needs to be square integrable. It's defined everywhere, not only on omega. And this is the so-called test function. It has 2 properties. It is non-negative, and it integrates to 1. Yeah, so mass 1 and non-negative. And with this, you can model a CCD sensor. So that's what's in your phones taking the pictures, right? It's accumulating the incoming light in little cells. And we can describe each of these cells with one of these functions, psi. If we do the following. We first define RH. Yes, please. Oh, why is this? Yes, you're right. What is happening here? Yeah, good that you mentioned it. Okay, I know what's happening. Okay, okay. So we define a function RH of x as follows. It is 1 over h to the d. And with h, think of the size of your individual sensors of your CCD sensor in your camera or smartphone, where x is smaller than h half, and otherwise it's 0. And then we can look at what is f with this test function. So we are moving this to a position x. And if we now insert all the definitions, we get this product and call this RH F. And let me make a picture so that's easier to understand what's happening. So let's say this is h half. Then we have a height of 1 over h. Yeah, so this function RH is just either 0 or 1. And the height is 0 or 1 over h. And the height is in such a way that the area here is 1. And what the scanning then does is, here's our 1D image F, and we now go to the position X. And this RH is like moved here. And then what it means to integrate this product is just to average F in this little space. Here, so this means this test function just mimics that your sensor has a certain width and all the intensity that falls in the sensors is just averaged. Yeah, it just gives us here the proper mathematical specification how you can model this. Yes? The no, this is the Lebesgue integral of these two functions. So in the case, so I drew an f that is also Riemannian integrable. So the Riemannian and the Lebesgue integral coincide in this case, but this is just a picture. So here we, what's incoming is any function that's Lebesgue integrable, and this, so the Riemannian integral is not necessarily able to integrate this. You're thinking about the, yes, so this is connected, you can think about this connected to the Riemann sum approximation for this special case, right? So this means that I take the function it's just shifted by x. Let me. So this notation means that we get a new mapping. Yeah, so it's a notation to take this function and move it over there. So I need a new function that is centered at x, and this is what this notation means. So this x is fixed. That's important. So we have to specify I want the value at pixel x, That's no, the x is here's the parameter. X is the parameter. It's here and it's here. Yeah. So this dot means that here is the free variable of the. Yes, but I'm integrating. Yes, I'm integrating in epsilon. Y. Yeah. Yeah. And also put y in here to get functions. Good. But really, if there are questions, no, I'm happy to discuss the notation. Right. I think it's very important that I'm not writing stuff that's not where you can't decipher what the notation means. H. Ah, yeah, yeah. Okay. Let me. Yeah, so when I describe the sensor, I need to specify what the width of this sensor pixel is and what the position of the sensor pixel is. And I just put it arbitrary on top and bottom. You could also put both on bottom, or it doesn't matter. That the area of the rectangle is 1, doesn't it? Yes, so this is h half, this is also h half, so the yeah, so I made the h half tick and here's the 0. That's yeah, so this is necessary to fulfill the integrates to 1 condition. And now, if we are given a grid X, so a number of these positions here, we can convert our F into a discrete image as follows. We take all these R H of F and we now go through these grid positions Xj. Yeah, so for every one of these cells, we take a psi that is 1 over h to the d in here to get the average value of f in each of the cells separately. So we convert the function into a discrete image. Yeah, and this can only be used to convert like continuous images into discrete images. You can also use this to downsample images, for instance. Yeah, if you want to halve the resolution or resample to a different resolution, you can use this too. So one final remark before we start with these point operations is something about coordinate systems that we briefly discussed 2 days ago, namely where the origin is and where the axis point to, because this is very different when you think mathematically about the unit square or when you have a pixel image loaded in MATLAB or Python. So we consider the unit square as our image domain. And then mathematically, the origin is in the lower left. Yeah, so this is what I implicitly assumed here. Here's 0, 0, here's 8, 0, and 0, 6. So that means in the lower left, I have the origin. But it's different if you have a digital image displayed on the screen. So there the origin pixel which would correspond index 1, 1. Yeah, so I started numbering the elements here in J from 1 to mi. So the first pixel that we have is 1, 1. If you think about C indexing, then you would, of course, have 0, 0. But with our notation, it's 1, 1. That is top left. Yeah, so whenever you take your favorite image processing program or image editor and open a picture, 1, 1, so the first pixel is on the top left. And also the axes are switched. So the first coordinate index corresponds to the vertical axis. And the horizontal, the second to the horizontal axis. So this is a rotation by 90 degrees, if you compare the two viewpoints. Yeah, so going back to that example, here's my origin, and now I rotate the entire thing by 90 degrees. So that means the first axis is vertically downward facing, and the second axis is horizontally rightward facing after the rotation. And you can do a lot of computations and manipulations of the image without ever noticing that these axes are handled differently internally. But whenever you compute angles, this is important. Yeah. But that's just an example. So it's an example that resembles roughly what they're using. So they actually don't use any true functions. You can think of the sensor as some array with small cells, and then there's incoming light, and the light ends up in one of these cells. And like everything in one cell is accumulated to one number. So it's just counting the photons that are coming into the cell. And this is modeled by just saying we average in a certain area. Yeah. So there is a close relation, but it's not exactly the same. Also, of course, I think there's tiny gaps between these sensors, so there would be some distance that you had to take into account. And I guess it's not perfectly square, but that's the idea. No, the height of the test function is just to get the average. But the sensors in reality do have a maximum capacity. So they can saturate, and if there's too much incoming light, you will just have pure white, even though, so you wouldn't see any contrast anymore. So you can easily verify this by playing with the settings of your camera app to have an overexposure. That is when the sensors are saturated. And this simple model here doesn't account for sensor saturation. Okay, so much for the preliminaries before we actually start with doing some small manipulations of the images. And the first thing that we're looking at are intensity transforms. So in the overview in the last lecture, I already mentioned that we will go through the different methods like by classes. Yeah, the first classes are point operations where one pixel is changed at a time without looking at other pixels. And these intensity transforms are point operations. Once we're done with this, we will move to these local operators and further to global operators who can more and more take into account the structure of the image. But so chapter 1 only is concerned with these point operations. And let me define exactly what I mean with intensity transformation. It's just a very simple mapping. So we start with an image. And here I can take a continuous one, but you can also think about a discrete one. And then T is what our intensity transformation will be. That's a mapping from R to R, so it can map one gray value to another. And we call this intensity transformation. And T composed with F, so that means at every point omega, I look at T of f of x instead of f of x. This is called intensity transformed image. So for there are a number of popular intensity transforms that I want to go through now. So I will first define all of them, and then we look at some pictures to see what the effects of these transforms are. And for the first one, we need to specify two numbers, a and b. And we define t clip of a and b, which goes from R to the interval a and b. And it's very simple. If we are at a position smaller than a, we map to a. If we are bigger than b, we map to b. And otherwise, we don't change the intensity value. Yeah, so it's like clipped to the interval AB. So it's a very simple profile. Yeah, it just is clipping the value range. So usually this is somewhat more specialized to a normalization. So T norm AB again goes from R, but now to 0, 1. This combines the clipping to the range 0, 1 with an affine rescaling. So this here makes sure that A is mapped to 0 and B is mapped to 1 and everything else is linearly interpolated. And this we call intensity normalization. So it looks similar. So this is this situation and that's the other situation. Yeah, except that A is mapped to 0, everything lower than A is also mapped to 0, everything bigger than B is mapped to 1, and B is mapped to 1. So here you have a good control then of the value range. And usually you choose A and B as minimum and maximum of f, so that you can rescale any image to the value range 0, 1. And since we have a continuous here, a continuous image, we should be a little bit careful. So when the image is not constant, the value range is closed and bounded. Then we get f hat, which is just t norm of f, and t norm of f without any interval specified here means that I'm using the minimum of f and the maximum of f as lower and upper range value. So this is value range 0, 1. And we know that the smallest value is 0, and 0 is attained, and the maximum value is 1. It's also attained. Yeah, that's why I need it. So this closed means that the largest and highest value is actually attained. And yeah, so with the boundedness, these values are finite, and then we can do the rescaling. Of course, if you have a discrete image, there are only finitely many values. That's trivially fulfilled. Yeah? So you can just use the infimum and so you can use the infimum and supremum here. I just need the closedness to get this. So that the minimum is, yeah, it's just a technicality. Yeah. Otherwise, you would have that the supremum is 0. The infimum is 0 and not the minimum. This here? This just indicates that this plot means this function, and that plot, yeah, I didn't want to write this T norm AB. So there are some other of these mappings. And the following one usually has a very different purpose. T theta threshold. It goes from R to 0, 1 and maps S to 0 if S is smaller than theta, and to 1 if S is bigger than theta. That is called thresholding. Yeah, for instance, this can be used for very simple image segmentation. Then all the larger values larger than theta go to the one segment, and all the ones smaller go to a different the other segment. But of course, yeah, it's very important to choose these threshold theta properly, and we will get to know one algorithm for this later. Probably not today, but in chapter 1. And for the threshold 0, yeah. Otsu, I think, is more the threshold is chosen locally, isn't it? It does it choose? Yes. Yeah. So that's so I don't remember if Otsu is really global or if it was local, but choosing this can be automatized. So choosing the threshold can be automatized, and there are different algorithms for this. So Otsu is one of those. But we will learn about the ISO data algorithm, which has probably a similar idea to Otsu. Yeah, but yeah, it's definitely important to how to choose, and you actually don't want to choose manually, but you want a proper algorithm to choose this for you based on some conditions that you want to be fulfilled. Okay. Um, so for the threshold theta equal to 0, this function is also called the Heaviside function. Yeah, and under this name, it also plays an important role in images other than in areas other than image processing. And the plot just looks like this. So there are some, so two more that I want to show. So the next one starts with a gamma. And this one goes from 0, 1 to 0, 1. So you can apply it also on all of R, but there it loses the properties that you want. So in S is just mapped to S, to the gamma. And this is called gamma correction. Yeah, and if you have ever played with tools like GIMP, you probably have noticed this gamma correction. And this can be like used to either pronounce the darker parts or the brighter parts. So and for gamma smaller than 1, this is strictly concave. And otherwise it's strictly convex. Also for a strictly bigger one, it's strictly convex. Yeah, we should also have a look at the plot. Here, this is gamma bigger than 1. That's gamma 1. And that's gamma smaller than 1. And what you can see here is that either you like distribute the areas close to 1 to a broader range and compress those close to 0, or you compress those close to 1 and expand those close to 0. So that means with gamma smaller than 1, you can see more details in the dark areas at the price of losing some in the bright areas. And if gamma is bigger than 1, you get more details in the bright, but less details in the dark areas. And I think I should have some pictures after I shown you the last of these transforms that I want to show. That's called T-log. And it goes from 0 infinity to 0 infinity. And it maps S to the logarithm with base 2 of 1 plus S. That's called the log transform. And this one is often used to visualize the so-called power spectrum. The power spectrum is the absolute value of the Fourier transform. Yeah, and we choose the logarithm for base 2 so that it maps 0, 1 to 0, 1 bijectively. But you could also use other bases. Yeah? Yes. Yeah. Unless you have really very big gammas. So the log transform allows you to catch really large values and bring them close to much smaller values. But that's a good point to switch to the examples. So we can look at this. So the first, which you can't see so nicely due to the lights, is this is a PET image on the left that I showed in the first lecture, and the normalization takes this grayish on at the background and puts this to 0, and the white just stays white because it already was 1. So this is just maximizing the contrast if you apply the normalization without like throwing away details or reweighting different areas of the contrast. Here you can see that clipping can be extremely necessary if you have outliers. And this is not the problem of the projector. This is what you get if you take the output of, this was from an electron microscope, and put it to the normalization. It turned out there was like 1 pixel with an extremely large value. And if the 1 pixel, or no, 1 pixel with an extremely small value, so that you see almost nothing. So you first, in this case, have to do some clipping to get rid of the outliers, and then the normalization, and then you see what's in these images. So that just should show that you need to be careful that sometimes just normalization is not enough if you have problems in your input data. Yeah, here's the example of the gamma correction of the different behavior when you are below 1 or above 1. Yeah, as I said, in the below 1 area, we should get more pronounced details in the dark areas, so which you can see here. These details on the feathers are more visibly, and if you have one value bigger than 1, then we should see more detail in the bright areas, but there are not so many bright areas here. Yeah. And finally, the this logarithm transform. So here we start with an image, again from electron microscopy, and it shows that one because this has periodic structures, and the power spectrum or the Fourier transform makes these periodic structures visible as like these streaks or these highly localized points in the Fourier transform. But so here is why the log transform is very helpful for this power spectrum. So if you first compute the Fourier transform and you subtract the mean value to ensure that the 0 frequency is 0, because otherwise it would be extremely high and overshadow everything else. So, but still normalization is not enough to, so on the lower left, I forgot that you don't see my mouse. So on the lower left, you see almost nothing. So you can tiny bit see of the streaks. And if you apply the log transform after that, it doesn't help you anymore. But if you apply the log transform beforehand and then do the normalization, you see much more details in the Fourier transform. Of course, you can also see there's a lot of noise that was completely hidden. And the reason is that these the values of these peaks are extremely much higher than the background. Yeah, and this is what gamma correction would not be able to give you unless you would adjust the gamma to an extremely large value that is exactly valid for this specific image. So you would have to adjust this large gamma value to different data sets, and the log transform does not have these problems. Okay. Yeah. Yeah, FFT is a fast Fourier transform. Yeah. Okay, that's for the next part. Yeah. So yeah, we don't know yet what the fast Fourier transform is, but that's one of the topics that we will cover. And at least for the visualization purpose, it doesn't make any difference. The fast Fourier transform can just be computed more quickly. It gives exactly the same result than the direct definition of the Fourier transform. Okay, so now we have seen a bunch of intensity transformations, and we want to think about what can we do with these kind of point operators. Yeah, because we are very limited, we may not look at pixel positions, but just at the individual values. So we can look at neighborhoods. But what we can do to construct these transforms is at least to look at the statistics of the intensity distributions in your image. Yeah, so the statistic is like a global information that you can compute once, and then based on that, construct some intensity transform. And the statistics are covered by the histogram. Yeah, and first, I would like to introduce the discrete histogram. And essentially, the discrete histogram is very simple. It just counts how often each gray value appears. But I'd like to formalize this definition, since this will also be helpful to extend the definition of the histogram to continuous images, where you can't just count, yeah, because you may have infinitely many times where a certain value is attained. So now let's start with a discrete image, capital F. With some value range V. Yeah, and discrete image was like we defined last time, so it's a D array for corresponding to a certain grid. And now we define the histogram of that image is mapping from the value range to the natural numbers, including 0. So this is doing the counting. And we map a value S to the amount of times we get that value in the image. Yeah, so for every value, like here we check whether every pixel has that value and count all the indices. It's really just counting the occurrences. And that's also not how you would compute it, but this is how you would define it. But what would be extremely inefficient for every value S to count and then count for the next value again. Yeah, but this is a very convenient way to define what the histogram is. Yeah. No, going back to the notation from last lecture, this capital F is to be understood as an array of values, and those values belong to the this index set I, and I call the entries of capital F, I call small f. Like with a matrix large F, you usually call the entries small f with the indices, and here I do the same. So there's no continuous image here. Yeah, but you're right, I didn't repeat the notation. Yeah, yeah, yeah. It's no problem. That's I like questions. Yeah. Also, she shows that you are somebody's paying attention, and I get some point across. Yeah? So, and this is now called discrete histogram of F. Yeah, and this just states how often does a value occur. And probably you can just, since I have it at hand, we can at least understand part of this. We don't know yet what GF is, but we can now see what HF is. So you can see there are a lot of very dark pixels on this cameraman, and that you can see in this red histogram. So there are high peaks for these small gray values. Yeah, so the height of these bars means the number of pixels that have exactly that value. And you can also see that the background, which has a bright grayish value, also is visible as peak in the histogram. So, and to get the connection to the continuous world, you can already make one preparation. With so-called Kronecker delta. which is delta ij. This is defined as 1 if I is equal to j, and 0 else. We can express the histogram as a sum. Oh, not defined. Because then hf of s is the sum over all our pixels, all indices, and I have delta s fj. Yeah, so at every pixel, this Kronecker delta encodes the check whether the value is s or not, and it's convenient to have such a sum representation instead of these count elements of a set representation. But also, this is for theoretical purposes. You would never compute the histogram by computing these sums one after another. And if we further specialize the value range, so for convenience, I just say it's 0 to n, but a finite value range is enough. We can define what this green curve in the picture was that I just showed to you. Then the discrete cumulative distribution function is defined as follows. Also CDF. It goes from this value range to the natural numbers, and it just counts how often the value smaller equal to s appears. Yeah, if we go back here, so the green curve, of course, has a different scale. So the values are not comparable, but you can see how the cumulative distribution rises rapidly if there are peaks in the histogram, or how it stays more flat when there are only few values. And yeah, these functions are helpful to like do manipulations of the images. One example that we will get is the so-called histogram equalization. So if you want to like uniformly use the gray values that you have available, you would like to have a distribution function that has a constant increase. So it's more like the identity, so that all of the gray values appear equally often. But we will get to that. So this histogram now can be extended first to pixelated images, yeah, which were those that are continuous but constant on each cell. So continuous in the sense that the domain is continuous. Of course, these pixelated images, their value jumps from cell to cell, so they are not continuous function in that sense. It's just a continuous domain. And yeah, to extend this to pixelated images, I will need to introduce some more notation. So we need characteristic functions and level sets. So for any subset A of Rd, I define chi A as mapping from Rd to 0, 1, and x is mapped to 1 if x is in A, and 0 else. So this is called characteristic function of A. Yeah, so essentially this is a way to convert a set into a function, but the viewpoints are equivalent. And now to the level sets. So we take a domain omega, and again an f from omega to r. And now for any value s, we define as short notation f equals s. These are those x in omega where f of x is s. And this is called S level set of f. And analogously, we have f smaller equal s. That was exactly the same definition, except that I replaced this equal to smaller equal. This is the s super no, the s sublevel set. F bigger equal s is the s super level set. Yeah, and let's try to make a picture. So let's say our function looks somewhat like this. Then the line here would be where f is equal to 0, and the interior would be where f is bigger equal to 0. So that would be the super level set, and the line, so the line would be the level set for value 0. There are some reformulations for this. So the pre-image of S, so F inverse of S, is the same as F equal S. So this is not like the inverse function, but the pre-images. So all points that are mapped to S. And the same or similar relations we have for the other level sets. The pre-image of the interval minus infinity to S is f smaller equal s, and along the same lines, the pre-image of s to infinity is this super level set. And we also have for d equal 2 and d equal 3 special names for these. So f equals s is also called level line or isoline. Or level surface, isosurface for d equal 3. Yeah, it really depends on which book you look at how these things are called. And so the last ingredient that we need to write down the histograms for the pixelated images is the volume. So for a bounded set A, I define like the absolute value of A as the volume of A, and this I just define as the integral over A, or equivalently as the integral over the entire Rd of the characteristic function. Yeah, so because that's only just 1 inside A. Yeah, so we are integrating the 1 over A, so this gives us exactly the volume. Yeah, and with this notation at hand, we can define now, or start to define, the histogram for pixelated images. So small f is a pixelated image, and capital F the corresponding discrete image. Yeah, so that means this f is constant in the cells, and this capital F is just the cell values as the array. So then we have the following, that we can now express the discrete histogram that we defined for the discrete image with the pixelated function. If we go back to this representation, yeah, so we had to sum over all the cells and needed a 1 inside a cell where the value S is attained by F. Yeah, and now I'm replacing this Kronecker delta here by an integral. So we take 1 over the volume of the cell Cj and integrate over the cell Cj the characteristic function of f equals s. So why is that the same? So we know, since f is pixelated, that it will be constant on the cell. So either f takes the value s or not, so that means this here is just either 1 or 0, and exactly like the Kronecker delta would be for our discrete image. So that means this is either 0 or the volume of Cj. And so I'm rescaling by 1 over the volume of Cj to make sure that it's 0 or 1. So exactly this is now just a much longer version of expressing this counting with the Dirac delta. But this now makes it possible to further rewrite it. So first, we notice that the volume of each cell is the same. And the volume of the cell is just the product of its side lengths. Yeah, just the product of these hj. So that means we can move this constant factor in front of the sum. And now we are just summing over all the indices over all the cells. That means we are integrating over the entire domain. So that this is the same as 1 over the cell volume times the integral over the characteristic function of f equals s. So that means we have just the volume of the level line here. Yeah, so that means except for the scaling factor, which we know is just the volume of the cells, the discrete histogram is the same as the volume of the level lines. Yeah, and the good thing is that this here we can look at for all kinds of functions f. They do not need to be pixelated. So this motivates the following definition. So now we will need a little bit of measure theory. So we just say that the continuous histogram could be a mapping from R to 0 infinity, and we just map S to the volume of these level lines. So it would be exactly the same counting that we did in the discrete case. So unfortunately, there's one problem with that. So this volume of these level sets could be 0. For all S. If we look at the extremely simple function, for instance, f of x equals x. Yeah, so the problem is that each S is only attained exactly one time, and the volume in 1D of a single point is 0. So that means that this kind of definition of the histogram wouldn't return anything for this image, which is certainly non-constant. Actually, it has a very, very nice shape. It's really the identity, and this should somehow correspond to the uniform distribution. Yeah, and no, for pixelated images cannot happen. So the pixelated images is fine. Yeah, yeah. So, but yeah. Now I want to generalize this, what we learned on the pixelated images, to the to arbitrary images. Yeah, because we already also want to make statements about continuous images. Because at the end of the day, a pixelated images is just a discrete approximation of some underlying continuous image. Yeah, this would also converge to 0. So if you no, so the point of also looking at the continuous world is that what you're doing is an approximation, a discrete approximation of reality, and you want to be able to say what will happen if you take more pixels. Yeah, next year the cameras will have twice as many pixels, and so you, or at least the mathematicians, are interested in what would be the limit. So what does this converge to? And for to describe what you could converge to, you need these continuous representations. Yeah, they cannot be finite. Yeah, so for discrete images we do this essentially, or yeah, so it's either this or the sum that's equivalent. Yeah. Which one? This one? So we take the sum here. So that means we are summing over all indices, and we have all these cells. So that means we are integrating here, we are integrating here, we are integrating here, and we're summing all that up. Okay, the thing before the integral. Right? So P means, so this is a product. Yeah. So yeah, you can't see that it's a capital pi. So in the lecture notes, it's unambiguous. You cannot mistake it for pi, but it's so it's just the product of the side lengths of our cell. So it's the volume of the cell. So, and I needed to rewrite this because I wanted to show that this is independent of this index. Yeah, because all the cells have the same volume. Okay, good. Yeah, so we have a problem now. This function cannot express the histogram of these kind of images, and unfortunately, no function can. So we need something that is more general than a function to describe what the histogram of continuous image is. And what is more general than a function? Yeah. Sorry. No, but it would also be, a series is also a series of functions, or yeah. But they all would have one value at one position. A distribution, yes, a distribution, or more generally, a measure. Because a measure not only maps like from one value to one other. So let me specify that. So we take exactly this idea here, but we make our input values more general. So we extend HF from R as domain to subsets of R. And not arbitrary subsets, but the Borel sets. So the set of Borel measurable subsets of R So what does that mean if you haven't looked at the appendix yet? So essentially, you start by just taking all the intervals, or all the open intervals, and then you have to do some closure to make a sigma algebra out of this, but you can think of intervals for now, so that we not only check if the value is s, but is the value in the range s minus 1, s plus 1, for instance. Because then we see something here. Then we can see that the different value ranges are actually attained. So that means we take this HF from the Borel sets to 0 infinity, and such a set is now mapped to the volume of F in A. Yeah, so this is more complicated to handle than a function because it's mapping sets now to numbers and not positions to numbers. But it is necessary to describe the histogram. Fortunately, the counterpart of the cumulative distribution function, this will stay function. There's sufficient to have a function. But first, let's note. Yeah, this is on how you can compute this. Oh wait, I forgot something. And I think I will end on that note also. So this H is now a positive measure. And to further understand this, we need to connect this to the cumulative distribution function. And the first thing that we note here is a different way to represent the histogram. So that's the definition, the volume of the set where F takes values in A. This is the volume of the pre-image of A under F. And this is, the volume is just the Lebesgue measure of A. And this shows that this HF is the so-called push-forward measure or image measure of the Lebesgue measure under the mapping F. And this is specified in proposition A8 of the appendix. And what this will show, and I will repeat this in the next lecture, it will show us how this measure can be used to integrate. or how you can compute the integration with respect to this measure without actually needing this measure. You just need to compose functions. Yeah, but here we will need what the push forward measure is, and we can look at that further in the next lecture next week.